Alrighty, welcome. Good morning, good afternoon, good evening, whatever time this video finds you. Today we are going to be looking at section 2.8 from your textbook, which is called the derivative of a composite function and the chain rule, which sounds kind of scary, but it's not. And in fact, this is probably one of the more important lessons in our entire book. The chain rule is something that is just so critical for being able to efficiently figure out derivatives. Because we're going to see in the lead up to the chain rule how it can get pretty dicey trying to calculate derivatives with the rules that we've discovered so far, which are basically the product and quotient rule. That they have serious limitations, especially when we start to look at some composite functions of higher orders and higher degrees. So the chain rule offers us an escape route, as it were, out of some pretty hairy situations. So with that little preface, we're going to jump in and see what do I mean by the chain rule, what do I mean by derivatives of composite functions. And basically the chain rule is how we do derivatives of composite functions. And once we start to see some examples, it starts to click pretty well, but it can be a little tricky at first. So I'll do my best to go slowly through this. Again, I would recommend if you're watching this at home, you can probably get away with 1.25 playback speed, which will cut your watch time by a quarter, which is something, because this will probably be a little bit lengthy. So let me switch over to my second camera, my document camera. Here we go. Here we are. I've got my pen, got my brain, most of it anyway, and we are ready. So this is, again, 2.8, the derivative of a composite function and the chain rule. And truly, the part after the ampersand, the chain rule, is the star of the show. The chain rule is just, it's one of the best tools we're going to have in our toolkit. So kind of reviewing my notes from last year on how I lectured this, I sort of followed the format of the book, but I decided that I hate that way. The way that it's laid out in the book is sort of just clunky and like, why, where are we going? So I'm going to change it up a little bit. I'm going to present the first example that the book goes through and hopefully convince you first that the rules of derivation, the rules of finding derivatives that we currently have, are insufficient for the particular function, or not insufficient, but lacking. I guess it's the same as insufficient. And then we will introduce what the chain rule tells us we can do and see that it makes our lives easier and in fact allows us to derive certain things. So the first thing that we're consider is a function defined as big F of x is equal to 4x cubed, 4x cubed plus 1 quantity squared. Close that off a little bit early. But we're live, so we can't go back. It's recording, it's rolling. Okay. Before we start worrying about what f prime might be, let's just note here that this is in fact a composite function. Note that f is a composite function. Okay. And I know you've dealt with composite functions prior to meeting me. The way that I think about composite functions is that there's an outer function and there's an inner function. I don't know if that's mathematically kosher to say it that way, but it makes sense in my brain. And so to me, the outer function here is the quadratic, okay? And we're composing it with this inner function, okay? So we've got, I've got like an attack of ants right now in room 412, so hopefully you guys aren't worried about ants. But so what really we have here is we have an x squared function, the quadratic function, but then we've shoved in this nasty looking cubic inside of it, okay? Hopefully you all see that, okay? So, and I'll even write it like that, outer function, let's say f of x is equal to the quadratic function, and our inner function, let's call it g of x, is equal to what's inside of our quadratic, which is 4x cubed plus 1. And so if we were so inclined, we could define f of x, big F of x, as f of g of x, that composite function, okay? So f being the outer function, x squared, g being the inner function. And that makes some sort of sense to us, hopefully. Okay, and that will come back in a minute. So first of all, that's a composite function. So let's see what happens if we just try to differentiate this according to the power rule, because this looks like, hey, it's a quadratic, let's do the power thing. So derivative according to power rule. Well, the power rule, let's do it like this, d dx of 4x cubed plus 1 squared. Well, the power rule says drop this like it's hot, drop down this exponent and subtract 1 from it. According to that, it would be something like 2 times 4x cubed plus 1. But like our spidey sense should kind of be tingling right now and saying like, that doesn't seem right. Like it seems like something about how this is changing should be affected by what's going on inside. And so to just deal with this outer function, to just differentiate x squared, I don't know, it just doesn't seem right as mathematicians, okay? And so if we go to our graphing utilities and try to scratch that itch, as it were, let's see what happens. Let's see what happens. Oh, hello, Steve.
Your webcam?
My webcam, class, my webcam is here.
And the speaker.
And my speaker.
Yeah, that's yours.
Thank you so much.
You're welcome.
Thank you. That's a big box for what I thought was going to be a small thing. Okay. So sorry for that commercial break for a new webcam and a speaker. So hopefully these videos, if they're going to continue, will be of higher quality now, because now we have, I don't know why this box is so big. Oh, that's a big honking speaker. Check that out. That's kind of fun. That's kind of cool. That's kind of rad. I feel like I'm in like a 40s radio station right now. Yeah, that's gonna be fun. So audio is going to hopefully increase in quality moving forward, but we're gonna stick with my webcam on my computer for now. So we're going to clear this jazz out, and we're going to say, okay, let's see what this curve looks like, and then do the ender on this guy and see if it's the same. And I'm kind of thinking it's not going to be, but who knows? Maybe I'm wrong. So first, let's see what 2 times 4x to the third plus 1 it looks like. So this is what like the power rule only will give us. And we'll go to our graph. Cool looking cubic looking deal. Whatever, we're not that impressed. We've seen cubics before. However, let's go back to y equals and see what happens if we do the numerical derivative. So math 8 derivative with respect to x of this original guy. Let's see if those two things match up. I don't think they will, but like I said, I've been wrong so many times before, so let's not get too discouraged yet. So I'm gonna do a starting parentheses again, and we'll do 4x raised to the third plus un, close that, and then square that. So we're letting the calculator do some work for us. We're entering the original function, 4x cubed plus 1 squared, and we're saying take the derivative of that everywhere. Remember, this could give us just at one point, but if we press x in here, that'll graph the whole thing. So let's see if this matches up. Still spinning, still spinning, still spinning, still spinning. Dagnabbit. Unless our calculator is lying to us, the thing we just computed here, the twice 4x cubed plus 1, is not what the derivative of that function looks like. So we see the need. We see the need here for some other thing because the product rule is failing us when we've got a composite function as part of that product situation. So I think now, so this is where I'm going to introduce the chain rule. I'm going to introduce the savior to the situation. And then we will kind of backtrack and see that it actually does match up with another way we could have computed this derivative. So the chain rule, enter Sandman, Q Metallica. I guess I could get like super weird with this stuff if I wanted to. Can I exit full screen? Maybe I can't do that. If I'm sharing my screen, I can't exit. Can I pause share and then do enter Sandman? No, we're not gonna do that. That's just gonna waste time. But in your heads, or maybe press pause now, go on Spotify, Metallica, enter Sandman, but it's gonna be enter chain rule. Yeah. I have no tune, so this could be a good vlog entry. Ohana. Chain rule. We're gonna go straight out of the book, straight out of Compton. 2.8.1. So actually, let's be clear here. According to TI 84, this is not the derivative of f. So whatever shall we do? Enter chain rule. Very dramatic entrance. Woo! Everybody's screaming, yeah, chain rule, yeah. Why are we cheering? I don't know. We don't even know what it is yet, but it's awesome, and we're going to be excited about it, okay? Enter chain rule. And the chain rule, according to Mr. Louis Lighthold, in definition 2.8.1, I guess it's a theorem. We're not going to prove it because it's a bear to prove. Oh, yeah, it's a bear. The chain rule gives us a way to deal with composite functions and their derivatives. Specifically, the chain rule says if the function g is differentiable at x, and the function f is differentiable at g of x, meaning whatever g of x is, you plug it into f and it's also still differentiable there, then the composite function f of g of x, which remind ourselves is f of g of x, just parentheses there in case you don't like the fog, is differentiable at x. And specifically what that derivative is, the derivative of that composite function is equal to, and it's going to feel kind of weird, but we'll do some examples and it'll kind of make more sense, is the derivative of f of g of x. That's what we just did. So just differentiating it like the outer function. But then the chain rule is, well, we also are going to bust out this inner function and multiply that, g prime of x. So basically, in like poor man's English, differentiate outer function, and then we also need to differentiate the inner function. So outer function, and then multiply it by the derivative of the inner function. It's beautiful. It's wonderful. It's life-changing. It's the chain rule. Okay. So we're going to differentiate just like the outer thing, like we would up here, but then we're going to actually do some trickeration, bust out that inner function, and multiply by that derivative. So kind of returning to our, maybe pause here and like let this sink in. The chain rule, just let it wash over you. It's broken. You're getting tumbled. You're panicking a little bit. I'm thinking of an ocean wave right now. If you've never been in that situation, you just gotta let it run its course. And then you slowly make your way up to the surface, kind of struggling for air. And then you burst through, take a big suck of air, okay? So we're back, we're okay. We've survived the first wave in this set. There might be another one coming. That's always the fear. But you're okay. We're all in this together. Here's our function. We did the first part here. We differentiated the outer function, but it didn't work. It didn't match up when we graphed it because we didn't do the chain rule, but now we will. So returning to f of x. Maybe let's box this up. I don't know. Somebody's rolling a cart through the hall and it's making me anxious. This is like very muy importante. Very muy importante. Yes, that's good English. Spanglish. Turning to f of x. f of x is equal to 4x cubed plus 1 squared. Can you guys hear that? I can hear that. It's okay, we'll let it pass. We'll let it pass. We'll let it pass. We'll let it pass. That's cool. That's cool. Oh, they got chalkboards running through the halls. That's why it's so loud. Yeah. So to differentiate f of x, we're going to redefine f of x as f of g of x, where f of x is x squared and g of x is 4x cubed plus 1. Cool, cool, cool. So then the chain rule to this now compositely defined function. I don't know if compositely is a word, but I just said it, so it works. Means that f prime of x will be little f prime of g of x times g prime of x. Okay, like we're still kind of uncomfortable with this, like a lot of moving parts, but we're gonna see it's really not that hard. We already did this first part. The first part is just taking the derivative up here, like we did. Just taking this like this is just x squared. And if this is just x squared, we just drop down the bottom part. Okay, one sec. I'm doing this during my normal cross-country periods. I've got a cross-country girl coming in who thinks we're about to do some stretching and core. So just hold on. Oh, I guess I can pause the share. Can I pause the recording? I don't know. We'll be fine here. One sec. You can fast forward through this. Hey, Paloma.
Oops. Did I join the wrong one?
Yeah, you're supposed to be with Maddie right now. I think she has a Google Meet set up.
Oh, okay, thank you, Coach Smith. Sorry.
No worries. I think Ella did the same thing. Hey, Ella. Oh. Ella, so we're doing a separate one with, oh, are you here? Are you here? Oh, she abandoned ship. She knew what to do. Okay, cool. Back to just me. Okay, so here's the moment of truth. We're going to take the derivative of the outer guy, which is just x squared. Just ignore the inner guy for now. And if this was just x squared, we drop this down, drop this 2 down, like we did. And leave alone everything inside. 4x cubed plus 1. The exponent is now, oh, can't see that, is now been decremented by 1. And now we're going to differentiate the inner guy, g prime of x. G prime of x, we said, was 4x cubed plus 1. Cool, cool, cool. Cool, cool, cool. So now let's do that differentiation. 2 times 4x cubed plus 1. We'll just leave that alone. The derivative of this guy, this inner guy, is the power rule again on this, which is 12x squared. The derivative of 1 is 0. So there's our derivative. Derivative of the outer guy times the derivative of the inner guy. Now let's go back to our calculator and see if when we plug this in, if that matches up to Ender. Let's see. Let's see. Because remember, just the outer guy, no dice. Let's maybe change this window here. No, we'll go back. Okay, so this was the one that didn't work. So let's fix it. This is the just derivative of the outer guy, but now we know we need to add in the derivative of the inner guy. So times 12x squared. We'll press graph and see if the magic happens. Fingers crossed. There's one. Still spinning, still spinning, still spinning. Hopefully the red curve matches up. Still spinning, still spinning. Oh, there it comes, there it comes, there it comes. Oh, yeah. I don't know if you can see that very well, but the red curve just came and laid exactly on top of the blue curve. And now the spinning has stopped. And we feel pretty confident that we've found the right derivative. Okay. The blue curve was that chain rule derivative. The red curve was when we let the calculator do it. I don't know about you, but I mean, we could change the window maybe and do that again, but I think we're okay. Let's do like -3 to 3. Let's zoom in a little bit. Do like -3 to 3. So the first one we see will be what we computed, and the second one will be the calculator. Cool. No, you can't. If I go closer, maybe you can see the color. That's blue. Watch, it's gonna get swallowed by the red. Oh, look at it, look at it, look at it, look at down, it's red. Ah, it worked. Look again, one. Everything happened for a reason. It's all good. Chain rule seems like it works. Okay. We're stoked. It's awesome. Life is good. Okay. But this beginning situation is still not complete, because we're going to confirm that I'm not just making the chain rule up, that it actually agrees not just with what the calculator says, but also with our previous method of finding this derivative here. Because there's a way to do this without the chain rule if we just let the square be a square and use the product rule. So let's confirm. Do I have room here? Probably not. We're going to flip the page and we're going to confirm what we just found. Let's confirm the chain rule result with the product rule. Let's confirm chain rule result another way. Another one. DJ Khaled. Yeah, okay. I just did that. I really just did that. So yes, I can physically feel the eyes rolling right now as you watch this sometime in the future. I know it's happening and I'm just okay with it, you know? I just don't care that much. Let's confirm the chain rule result. Let's confirm chain rule result another way. It's not even the right phrase. It's not even another one. It's another way. Smith, you're the worst. Yeah, I know. Okay. And the other way we're going to do it is with the product rule. So f of x is equal to this composite function of 4x cubed plus 1 squared. But we can kind of like uncomposite this function and just make it a product. Because really this is just 4x cubed plus 1 times 4x cubed plus 1. So the 2.2 way to do this problem, is that where we learned this? All right, no, 2.3, is to say f prime of x can be found, big F prime of x, by using the product rule, okay? And saying the first guy times the derivative of the second guy times the second guy times the derivative of the first guy. So this will be 4x cubed plus 1 times the derivative of 4x cubed plus 1 plus this whole mess again, because it's like the same first and second function. 4x cubed plus 1 times the derivative of 4x cubed plus 1. And let's not even compute this just yet. Let's just take a deep breath and see what's going on here. Well, it looks like I've got one situation with 4x cubed plus 1 being multiplied by the derivative of 4x cubed plus 1. And then I'm adding it to the same exact thing. So really I've got two of these going on. This might be the weirdest like term you've ever seen. Maybe it's not, but these are like terms. I got two of these things. Let's make that look nicer. This is really two of this whole mess. 2 of 4x cubed plus 1 times the derivative of x with respect to x of 4x cubed plus 1. Where have we seen this before? Like 3 minutes ago. Or maybe longer. I talk a lot. We saw that right here. What? It's chain rule. Product rule is confirming the chain rule. Oh. And so now, finishing this out, 2 times 4x cubed plus 1. The derivative here of 4x cubed plus 1 is 12x squared. And so just doing the product rule gets us to what the chain rule told us it should be. So some smart aleck in the back now is probably thinking, well, why do we need the chain rule if we've got the product rule? Well, okay, sassy Sam back in the back of the room. I don't think we have a Sam in this class, so I can say that. Well, sassy Sam, the reason we want the chain rule in some situations and not product rule is first, this was like kind of difficult. You had to remember the chain or the product rule. The chain rule is kind of just like easier to remember in my brain, but it's not always going to be a square here. What happens if it's like something super hairy or not even that hairy? Like, let's just say it's something like the fourth power. May the fourth be with you. It's not even close to May 4th, but still. What about something really hairy? Okay, so the question from Sassy Sam, and I like that name because it's androgynous, so I'm not picking on a boy or a girl here. It could be anybody. Sassy Sam. Is that, so the question is, so why use chain rule? Says Sassy Sam. Well, I'll tell you why. Consider something truly hairy. What happens if big F of x is equal to something like 2x squared plus 3 to the 4th? In the grand history of mathematics, this is really not even that hairy when it comes to composite functions. We could get way, way, way hairier. I'm talking like Steve Carroll, 40-year virgin style. Okay? Could get super hairy. This is not that bad. But without the chain rule, it's pretty bad. Okay? So let's first do it the easy way. Let's see what the chain rule says. Chain rule. Okay? Chain rule way. And I'm gonna, for the first few times, be like explicit with the outer and inner functions until we get kind of a sense of what's going on. So chain rule, we'll let f of x be equal to little f of g of x. And we'll say that the outer function f of x is the quartic function. That's always been a weird word to me. Quartic. And the inner function g of x is equal to 2x squared plus 3. And so to differentiate this bad boy with the chain rule, f prime of x, according to the chain rule, will be the derivative of the outer function times the derivative of the inner function. but kind of the caveat here is the derivative of the outer function still keeps the composite nature. So by that I mean our derivative here of the outer function, we're going to pretend this is x to the fourth. This would become 4x cubed, but we've still got this composite piece. So the 4 drops down, becomes a 3, but still with all this mess inside. So we get 4 times 2x squared plus 3 cubed, and then differentiating the inside guy, g prime of x, g of x being this guy, we multiply this by 4x, because the derivative of this is just 4x. 3 goes away, 2 times 2 is 4, 4x. Okay, so take, and this was even kind of doing it like the long way, just take in, waft in how nice and smooth the finding of that derivative was. 2 lines, maybe 4 if you're being generous. Okay, we've all taken a moment to waft. I'm serious, waft it. That's nice, that's easy, that's fun. So Sassy Sam, you're about to eat your competence. Come up at, I've never known how to say that word. You're about to get your what for to find out why the chain rule is better than not the chain rule. We're gonna take a deep breath here because this is not gonna be fun. Not using the chain rule means that we have to use the product rule on this. Oh yeah, you asked for it, Sam. I actually had a student named Sam last year, so this would not have worked as well. So f of x, big F of x, is equal to 2x squared plus 3 squared times 2x squared plus 3 squared. So we're first going to treat this as like just a product rule, but we're going to see pretty quick there's like product rule inception here that's going to just confuse you more than that movie did. So deep breath. Product rule, f prime of x is going to give us the first thing, 2x squared plus 3 quantity squared times the derivative of the second thing, 2x squared plus 3 quantity squared, plus 2x squared plus 3 squared times the derivative of 2x squared plus 3 quantity squared. Okay. Oh, we don't like this already. But we can kind of be, we're going to even do it the not awful way. I've done this in the past where like we actually find this derivative as we go and then combine stuff, but let's at least be a little bit smart here, and it's still not going to be that fun. Kind of like we just did up here, we now have identical terms here. They're very weird looking like terms, but these are the same. This plus this is 2 of thises. So I'll say that again. This thing plus the same this thing is 2 of this thingies, which means we can write this as 2, and I don't even know what kind of bracketing symbol we use here. Let's do like big bracket. We've got 2x squareds plus 3 squareds times the derivative of 2x squared plus 3 squared. Small bracket, big bracket. We still haven't figured out this derivative. There's another derivative we have to do. Okay, so let's keep going. So 2 times 2x squared plus 3 quantity squared. We're now differentiating another product. And this is a square in here. That's a square in here. Way there. So this is 2x squared plus 3 times 2x squared times 3. So this is going to be 2x squared plus 3 times the derivative of 2x squared plus 3 plus 2x squared plus 3 times the derivative of 2x squared plus 3. Oh, okay. Let's make sure we're keeping track of everything. I think we're okay. We product ruled this thing, and they expanded into this thing is blowing up fast, but we're keeping a handle on it. We're okay. So we're again going to recognize that these are the same thing, and so we can write this as two of these things. So this is still 2 times 2x squared plus 3 squared. We're now going to say inside here, we've got 2x squared times 2x squared plus 3's times dx of 2x squared plus 3. Oh. Do you regret anything yet, Sam? Because you should be, because this is way harder. They're just not as fun. Okay, so we're almost home free. Okay? We've almost arrived where we need to arrive at. I'm gonna do a couple things at once. Am I? Yeah. I'm gonna slide this 2 out front because this is all just a product. You can multiply things in whatever order you want. That's like first week of Algebra 1. Don't let this freak you out. So these two we can multiply to become 4. This 2x squared plus 3 squared times another 2x squared plus 3 can be written as 2x squared plus 3 cubed. That's the power of exponents to write things more condensed. And then we will finally take this derivative here. The derivative of 2x squared plus 3, we know how to do, is 4x. So that does agree with the chain rule. So it's another verification that the chain rule works, but it's also an answer to the question, why use the chain rule? Because for any composite of a power function bigger than like a square, and even the square, even the quadratic composite is not that fun, but for sure for higher order powers, this process becomes unbelievably complicated. And the chain rule saves us from that unbelievable complication. Okay? The chain rule allows us to attack composite functions in a very smooth way. Okay? So we'll jump straight into one that we would just have no chance, well, not no chance, just we would never want to do the product rule by, and we'll call it illustration 4. We've already skipped 3 illustrations, but that's okay. So maybe take a pause here, celebrate we made it through 2-ish examples. But we're going to keep on trucking. This is a psychotically long lesson. It's not that bad. It's pretty bad. But we're okay. We're dolphins. Fins up. Illustration 4. Let's say, this is kind of weird. They give it to us as 2 functions. And do they? I don't know. Yeah. So I just got kicked off Zoom. I'm hoping it's still recorded. I don't know. It says it's recording. That happened a little bit earlier today, and when I came back, all the students were still here. So if this didn't work, I'm gonna be super sad because this has been 45 minutes of my life that I'll never get back. But it's okay. I love the chain rule. I love math. I love talking to an empty camera. It's all good. We're cruising. So let me go back to the view, not the show, but the view that I want. Whew. So hopefully you got all this. If not, press pause and copy it down. So I don't know where it cut out because I just looked up suddenly. I think not that long ago. We were confirming that the chain rule is actually super tight and awesome and worth our time. because we had a sassy student in the back of the classroom yelling, why not just use product rule? And we showed that person, that gender neutral person, that the product rule, even for a 4th degree situation, is like a lot of monotony. And this is just smooth and fun and, dare I say, sexy. You know, it just works. So we're going to see now that if we have super nasty, like x to the 10th, chain rule all the way for the dub, and g of x equal to 2x cubed minus 5x squared plus 4. And we let some composite function, big F, be equal to f of g of x, which sometimes is helpful to think of as f of g of x. And then, of course, we need to find f prime of x, the derivative of f. So just for a moment, just picture how awful it would be to do this for x to the 10th. Can you even? I can, but I don't want to. It would just be like a mushroom cloud of expanding terms, and it would crush our spirits and our souls. We very well might die in the attempt. It's that difficult. And so then enter chain rule to save the day. Okay, because the chain rule means that if f of x is equal to f of g of x, f prime of x is equal to the derivative of the outer function times the derivative of the inner function. So, I guess we should write f of x. Yeah, that would be helpful. So we're trying to differentiate 2x cubed minus 5x squared plus 4 to the 10th power. Oh my gosh. Enter chain rule, and our life all of a sudden just unfolds before us in harmony, and everything's okay with the world. So the derivative of the outer guy is power rule, x to the 10th. Drop that down, that becomes a 10 in front. You've still got 2x cubed minus 5x squared plus 4. We drop the 10 down, we subtract 1, that's a 9th now, times the derivative of g, which is dx of 2x cubed minus 5x squared plus 4. And then simply taking that derivative, 10 times 2x cubed minus 5x squared plus 4 to the 9th. The derivative of this guy is 6x squared minus 10x, and we're done. Oh, so easy. So stoked. So stoked. The most stoked we've been all day, maybe. That was illustration 4. Should we mess around with some harder stuff? I suppose we could. Which ones do we want to do? Which ones do we want to do? We could throw some trig stuff in here. Yeah. Everybody's favorite thing is trig, right? Trig stuff engaged. This will be illustration 5. Okay, and we're going to keep for at least a couple more examples doing the like here's f of x, here's g of x, f prime of x times, but then eventually we're just going to look at a composite function or look at a function, identify that it's composite, and know, hey, this is chain rule situation. This is chain rule territory. We better do chain rule. So I'm being kind of deliberate because the book is deliberate, and I think it's a good practice to see what's going on. So and I'm going to do a little backwards here so that we start to identify these things. Let f of x equal the sine of x squared plus 3. Find f prime of x. Okay. So here we're looking at a function and asking ourselves, is this composite? And the answer should be yes. We've got an outer function of sine, an inner function of x squared plus 3. So if we wanted to do that deliberate thing, we could say, let the outer function f of x be sine of x, and g of x, the inner function, be x squared plus 3. Then f of x is in fact a composite function, f of g of x, and therefore the derivative of f, big F, is f prime of g of x times g prime of x. Chain rule. Okay. More specifically, f prime of x is going to be, how do we write this? Can we write this? Can we write this? Yeah. So it gets a little trickier with trig stuff, but we're okay. So the outer function is sine. So the derivative of the outer function is the cosine, still with x squared plus 3 inside, times the derivative with respect to x of the inner function, x squared plus 3. And so this turns into the cosine of x squared plus 3. This derivative is just 2x. And so we would write this as 2x times the cosine of x squared plus 3. Not too bad. Not too bad at all. Okay. So now we're just gonna like jump in and do a handful of examples and see how we do. So we're almost an hour in. How do I want to pace this? I'm just gonna keep talking because I'm feeling good. Let's just do this. And if you don't watch the whole thing in one sitting, that's on you. So we're gonna call this illustration 6. Yeah, illustration 6. Yeah. Seems what should come after illustration 5. Crazy that none of these are actual examples yet. Saving the good stuff till the end. Illustration 6. Ooh, okay. If h of x is equal to 2 over x minus 1 raised to the 5th power, find h prime of x. Okay. This will be the last one that I explicitly do the f and g, the f of x and g of x situation. But the outer function here would be x to the 5th. The inner function here would be 2 over x minus 1, which I think we'll find useful to think of as 2 times x minus 1 to the negative 1. I think. Okay. So in other words, h of x can be thought of as f of g of x. And therefore, h prime of x is chain rule town. Chain rule territory, f prime of g of x times g prime of x. Cool, cool, cool. So that means that h prime of x, taking the derivative of the outer function, will drop down this 5 times 2 over x minus 1. The 5, we subtract 1 to get to the 4th. And then we're going to be taking the derivative of the inner function, 2 times x minus 1. Now, you are welcome to keep this as 2 over x minus 1 and use the quotient rule. Totally fine. But as we'll see in an example in just a second, now with the chain rule, I'm almost going to say that every time we have a rational function, especially with a constant up top, we should be thinking, turn this into a negative exponent and use the chain rule. So by that I mean, turn 2 over x minus 1 into 2 times x minus 1 to the negative 1. Because now we can power rule this and use the chain rule in here, which in this case won't be that interesting because the derivative of what's inside is 1, but we'll see in a second it can get interesting. So this turns into 5 times 2 over x minus 1 to the 4th. Check out this derivative. We're going to drop down this negative 1 to make this negative 2. So we're actually doing a chain rule again here. We're taking the derivative of the outer function. This becomes a negative 2. And then we are doing the derivative of the inner function as well, but it just so happens in this case that that inner function has a derivative of 1. So cleaning this all up, we get 5. I'm going to write this as 16 over x minus 1 to the 4th. This will become negative 2 over x minus 1 squared. The derivative of x minus 1 is 1, so that goes away. And this all turns into negative 160 over x minus 1 to the 6th. Pretty cool. Okay, so we were able to use the chain rule in one of these intermediate steps to do this rational function. And as we'll see in what has finally become example 1, and this might be our last hurrah for right now because I'm running out of steam. And there's plenty more to do in a second lecture, so we'll break this into 2. Yeah, that's fine. We're going to see that one of the big uses of the chain rule is turning rational functions into power situations where we can apply the power rule. What do I mean by that? Well, I mean example 1. So if f of x is equal to 1 over 4x cubed plus 5x squared minus 7x plus 8, and we are asked to find f prime of x. There is certainly nothing inherently wrong with using the quotient rule here. You're not going to get thrown in jail. They're not going to deport you. I don't know what they do to people who do weird stuff in math, but it's not going to happen. Okay? You're okay. But hopefully I can convince you that rather than trying to remember the dn minus nd over d squared or whatever, you can just use chain rule. Chain rule, chain rule, chain rule. How? By realizing that f of x can also be written as 4x cubed plus 5x squared minus 7x plus 8 to the negative 1. Bum, bum, bum. And now this is a composite function. Our outer function is x to the negative 1. Our inner function is this whole mess. It's time for the chain rule. Boom, roasted. So f prime of x, the outer function derivative, means dropping down this negative, keeping the inner part intact. This negative 1 becomes a negative 2. And then we're going to differentiate the inner function. 4x cubed plus 5x squared minus 7x plus 8. And let's see what happens. I'm going to do two things at once here. Am I? No, I'm not. Am I? No, I'm not. Yeah, I am. I'm going to throw this bad boy down into our denominator. So this will become 4x cubed plus 5x squared minus 7x plus 8 squared. And then we'll deal with the top. This is going to be the opposite. So we have this negative from when this dropped down. Negative 1 dropped down. So it's really like a negative 1. And now it's just an opposite. Opposite of whatever this derivative is. Going term by term, 4x cubed becomes 12x squared. 5x squared becomes 10x. Negative 7x becomes negative 7. Positive 8, 0. And then applying this opposite, we get negative 12x squared minus 10x plus 7, all divided by 4x cubed plus 5x squared minus 7x plus 8 quantity squared. That is f prime of x, which is what you would have gotten if you had done the quotient rule, but it might have just been a little bit more clunky. Might have been a bit more clunky. Okay, I think that that is a proper place to press pause, or in my case, press stop on the record button. And make sure that whatever homework assignment I come up with and post with this, you get that done. And then bring questions with you to class so we can talk about them. All righty. See you soon. How do I stop recording? Stop recording.